All right, here's another video on integration by parts. In the last video, I introduced this technique, integration by parts. In this video, I just want to go through a whole bunch of examples. The idea that repetition is really what's needed when you learn these new techniques. So in the last video, we came up with this formula. It's a good formula to have memorized. It's the integration by parts formula. And we'll use that formula in all the examples we do in this video. So this first example, we're asked to find the integral of x squared cosine of 5x dx. And the way I like to do these is first recognize that you have a product of two functions here. The function x squared and the function cosine of 5x. And what you want to do is determine which of those two things should you set equal to u. And once you decide which one of those two things you'll set equal to u, by process of elimination, the other one will be your dv. And then once you know u and dv, you can figure out du and v, and you'll have all the parts necessary to use this formula. So I always start by figuring out u. And your book gives you like an acronym. I've seen this in a few different places for how you determine what u is. It's ILATE or LIATE, depending on which book you use. And the idea is it's supposed to give you an order that you choose what u should be. The problem with choosing u based on that acronym is you can always come up with the counterexample. Right? You trust this acronym. Here's the counterexample. Oh, it doesn't work anymore. We'll change the acronym to this one. Well, then this counterexample doesn't work anymore. So rather than just kind of blindly trust an acronym, I never even learned that acronym, frankly. I didn't even know it existed until I started teaching. What I do is I just look at this problem and I remember with integration by parts, what I'm going to do is I'm going to change the integral of u times something into the integral of du times something. So I think about, of these two things here, which one gets easier, loosely speaking, when I take its derivative. And the thing that kind of simplifies when I take its derivative is the x squared here. Let me show you. If we let u equal x squared, well then du over dx, the derivative of u, would be 2x, and therefore du would be 2x dx. And by process of elimination, if this part is the u, everything else is the dv, so cosine of 5x dx would end up being my dv value. Note that I still need to figure out v, and v is the antiderivative of cosine of 5x. And you'll probably get to the point where you can figure out the antiderivative of this guy just by looking at it. And so maybe I'll do that the first time. But if you have a hard time just going straight from here to v, then what you can do is kind of off to the side, use one of our techniques of integration. And specifically in this case, I think substitution will work for you. But I think you'll get to the point when you get good at these that you can figure this out without substitution. And let me try to talk you through how. So I want to end up, when I take the derivative, with the cosine of something. Remember that the derivative of sine of something is cosine of something, so it kind of makes sense that I'm going to have a sine of 5x right here. But if I tried to make this v, there'd be a problem, because think about what happens when you take the derivative of this. I'd have to use the chain rule. The derivative of the outside function, the sine of the stuff, would turn into cosine of the stuff, but then I wouldn't be done. I'd have to multiply by the derivative of the stuff. The derivative of 5x is 5. So if this were my function, my derivative would be 5 times cosine of 5x. But I don't want a 5 times cosine of 5x. I just want a cosine of 5x. So I better put a 1/5 out in front here so that when I get that 5, it cancels out with this 1/5 and leaves me with just the cosine of 5x. What I'm saying is that if v is 1/5 sine of 5x, then dv is cosine of 5x dx. If you don't like that, that kind of playing with the pieces and sort of tweaking it a little bit until you can figure out something that works, what you could do is say, well, I got to figure out what v is. V is going to be the antiderivative of dv. So v is the integral, the indefinite integral of cosine of 5x dx. How do I figure this out? Well, how about u substitution? What if I let u be equal to 5x? Well, if u is 5x, then du is equal to 5 dx. And if du is 5x, then a fifth of du is equal to dx. So I can go plug in all these in and say that v is equal to, let's see, instead of the dx, I'll change it to du and I'll have a 1/5. Put that 1/5 out in front of the integral just to save myself a step. And then in the integrand, I got the cosine of 5x, but 5x is just u. So I have the cosine of u du. And I take the antiderivative of a cosine of u. Well, that's really easy. The antiderivative of cosine of u is just sine of u. And then plus c if you want. But then I'm not done. I have to change my u back to what I did the substitution for, which was 5x. So I would say I have 1/5 the sine of 5x plus c for the antiderivative of v. When you figure out v here, you don't need to put in the plus c because all the different constants that you have throughout the problem can be kind of added up at the end. So, well, you could put a plus c right here if you really wanted to. I typically leave it off. I think everybody typically leaves it off when they figure out v. Work through the entire problem, and then remember to tack on your plus c at the end. At any rate, once you have these four pieces, you can use your integration by parts formula. My integration by parts formula tells me that the integral of u dv, so the integral of x squared cosine of 5x dx, exactly what I have written right here, is equal to u times v minus the integral of v du. Something that always bothered me with this formula that may or may not bother you is when you're writing your answer here, v shows up twice and dv never shows up. So you write all these pieces and maybe you write four pieces and you need four things to go into your formula, and you might expect to use each thing once, but you actually don't. You use v twice and you don't use dv at all. You're like, why do you even figure out dv? Remember, that's part of the question. dv is defined for you and you use that to figure out what v is equal to. At any rate, here's u, here's v again, and here's du. This first time through, I wrote things in the exact order that they're presented in, just to try to make it easier for you to follow the formula. But if I were doing this on my own, I probably wouldn't write it in this order and would instead write this line here. I like to have my coefficients out in front, so this 1/5 I would have written it first, and then x squared sine of 5x. That's just aesthetics. I think that's prettier. Over here, I got a 1/5 and a 2 that are both constants, so I would have pulled those out in front of the integral right at the start, rather than writing them once and then pulling them out. And then I like to have the x before the sine of 5x, again, just aesthetics. I think that that's prettier, so I write it looking this way. And now you've done integration by parts, and you're like, okay, cool, I'm done, right? No, you're not done. What you did is you changed one question into another question. Think about the integral as signifying there's still work to do. And you're like, oh, right. But usually what I do is I use integration by parts, and that leaves me with an integral that I can take the antiderivative of. So what's the antiderivative of this guy? And you stare at it, and you think, and you pause, and you give the student time to think. Maybe you just stop talking. And then you realize you don't know how to do it, right? U substitution ain't going to work, and you don't have a method for figuring this out just using our basic methods. What are you going to do? Well, it's a product of two different things. I got an idea. Since it's sometimes something else, what if I used integration by parts again? And you can almost see what's going to happen, right? We'll have to choose which one of these things should be u. Think about what you want to be u. If your u is this x, your du is going to be real nice. And that'll make it so we have 1 times something, so it's less of a product. Let's try it. If I choose to let u equal x, and if you didn't know how to do that, you could try letting u be sine of 5x and let dv equal x. And what you'll see when you try it is the problem gets harder, not easier, so you're kind of not heading in the right way. But it's not immediately obvious what u should be equal to. That's the purpose of this video. We're just doing examples to get you some repetition. Anyways, if u is x, then dv has to be equal to the sine of 5x dx, kind of what I have left here. And when I take the derivative of u, I get 1. So therefore, du is just 1 dx, or just dx if you want. And to figure out v, well, yeah, you could use u substitution again. But if you just figured out that this dv leads to this v, you might be able to figure out that this dv leads to this v in kind of a parallel fashion. I'm going to need this 1/5 to counteract the 5 that I get when I use the chain rule and take the derivative of 5x. And then sines and cosines, there's kind of a loop going on there. The derivative of cosine is negative sine, so I need this negative out in front here to get this value of v. Note that I indented this a little bit. There's options. There's lots of different styles that people use. Sometimes what I'll like to do is not write the entire line and just figure out this integral maybe in blue. So maybe I can even denote to the reader that what I'm doing is working on this part. I'll get this answer in blue, and then I'll write the entire line out. These problems, when you use multiple iterations of integration by parts, can be kind of ugly. Another option is just to write the entire line the whole time going down, and either way is totally fine. It's just a matter of preference. At any rate, I want to take the integral of this guy. The integral of u dv equals, per this formula, uv minus the integral of v du. Here's my u times my v. Notice I jumbled the orders up a little bit. Instead of writing this line and then this line, I jumped straight to the second line. And then here is my minus v du. And you're like, oh, you screwed up, man. You put a plus here, not a minus. Right, but if I'm subtracting v du, there's not much with the du, that's just the dx. And since the v is negative, I can take this negative 1/5 and pull it out in front of the integral sign. And so I'm subtracting negative 1/5, which is the same as adding 1/5 times this thing. And the good thing here is now, since we've done 2 iterations of this, we've finally gotten ourselves to the point where you can stare at this integral and just figure out the antiderivative. In fact, I think we've already done it, right? Way up here, when dv was cosine of 5x dx, figuring out v was identical to figuring out the integral, indefinite, of cosine of 5x dx. What I'm saying is I can replace this with 1/5 sine of 5x. Note that instead of writing 1/5 sine of 5x, I took the 1/5 and multiplied it by the 1/5 to give me this 1/25. And now that I don't have any integrals left, I'm pretty close to done. I tacked on the plus c, so I don't forget to put on that plus c there. Just be careful. Note that what you figured out is really just the blue box here. So my final answer, maybe in red, would look more like this. I have this negative 2/5 times this integral, which is the box in blue. So I copied all the stuff in blue and put it here. And you're like, liar, you didn't copy all the stuff in blue and put it here. You put the c outside the parentheses for some reason. And again, that's just because negative 2/5 times a constant is just some other constant. So you can always just kind of move the c's way out to the end. This is a perfectly acceptable answer. You're totally done here. But I think most people would not leave their answer there. It kind of looks weird to have this negative 2/5 and then also have these coefficients in here. I think most people will take the negative 2/5 and distribute it into the parentheses. If you want to do that, you can, and I'll write what that looks like. But before I do that, I want to make the point that you got to be really careful with the parentheses. When you're using these formulas, you often end up with a sum or difference of two different terms. So when you do this twice, if you have a coefficient out in front of this integral, then that coefficient has to hit each of the different terms that you end up with from using integration by parts. So if you're not really careful with these parentheses, the negative 2/5 will just hit this first term and won't hit this next term. And that can be really frustrating, especially when your homework is computer-based, and just missing a set of parentheses is enough for the system to get really mad and say that your answer is incorrect. If it were me and I put a lot of value on how pretty an answer looks, I'd probably take it one more step and write it this way. And you might notice there's some pretty interesting patterns going on here with the sine and then the cosine and then the sine and 5 and then 25 and 125 and different powers going on. That's all true. I'm sure you could spend forever looking for different patterns and finding formulas for these guys, but really I wouldn't spend too much time on it. I just make the point that integration by parts, sometimes you'll have to use it multiple times within a single example.